have an analysis to find out the meaning of the neighborhood counting, we can do an analysis. So, okay, so we have a data space like this, which is defined by a number of variables. And we have a data space, neighborhood space, and the neighborhoods may be small, neighborhood space may be small. For example, so this neighborhood space may consist of only two elements. One is the empty set, another one is the whole set. So that is the simplest neighborhood space. But the neighborhood can be colossal if the neighborhood space is the power set of omega. But conceptually, we can still index the neighborhood. We can still index the neighborhood if omega is finite. We can index the neighborhoods in this way: the first neighborhood, the second neighborhood, and so on. And for any data points from the data space, we can create the representation vector in this way. So each element corresponds to a neighborhood, and the values of this vector is defined in this way. So it is 1 if the corresponding neighborhood is a neighborhood of this T. Otherwise, we have 0. So as a result, any data points can be represented as such a vector, 0, 1 vector. Okay, and now we consider two data points, G and H, and their representations being these ones, being 0, 1 vectors. Then the number of neighborhoods for one data points for G can be simply calculated in this way. We self-multiply this vector. That will give us a count of neighborhoods for each element. And this is the same for the H elements, and each neighborhoods can be calculated in this way. And the number of common neighborhoods for G and H can be calculated simply by multiplying the two vectors, which is like this. And we can even normalize this number in this way. And actually, this turns out to be the cosine similarity of the two vectors G and H. Okay, and then the neighborhood counting similarity has a derived distance. So we can define a distance function in this way. Okay, so for two data points, G and H, and then we can define a function like this. We can represent each data point as vectors, and then we have such an expression. And this one turns out to be the Euclidean distance between the two vectors in the vector space. Okay, so that is actually the Euclidean distance in the vector space. So the meaning of this distance is, so it is the number of non-common neighborhoods in both data points. So remember the similarity. The similarity means the number of common neighborhoods, but this one means the number of non-common neighborhoods in both data points. Okay, so the neighborhood counting similarity has some nice properties. So it is a similarity metric because we can easily, based on that analysis, we can easily show that it satisfies the similarity axioms. And the NCS is also a kernel function because it is a product of representation vectors, as I showed earlier. It is the product of representation vectors. So as a result, NCS can be used in kernel methods, such as the support vector machine. It is also generic in the sense that it is defined using the general notion of neighborhood, and which is valid for any data, any type of data. So the NCS is applicable to any type of data as long as neighborhood can be defined. For example, for multivariate data, which is defined by a number of variables, a neighborhood can be defined as hypertuples. I'm going to show this later on. And for sequence type of data, and the neighborhood can be subsequences. And for tree data, the neighborhood can be subtrees. And for graph data, the neighborhood can be subgraphs or even path. So there is flexibility in the notion of neighborhood. Okay, in summary for this part, so we know similarity or distance is important in machine learning, and in both classification and the clustering, similarity function play an important role. We know that for a fact. And the NCS, neighborhood counting similarity, can actually serve as a methodology for devising new similarity measures. So if you want to devise a new similarity for a new form of data, then you can use the NCS as a methodology. But if you want to incorporate new constraint in your existing type of data, and you can also use the NCS as a methodology. You can start with NCS, and then you can define your type, your neighborhood, and then you end up with a new similarity measure. So it is a methodology. And as a generic similarity kernel, so the NCS is conceptually uniform in handling all types of data. It is simply a common neighborhood counting. So it is efficient to calculate when neighborhoods are specialized for a type of data. And the NCS has a nice mathematical property, as I showed earlier. Okay, moving on to the next topic, neighborhood counting similarity for multivariate data. So this is actually one specialization of the generic similarity data for multivariate data. So the motivation is fairly simple. We want to specialize NCS for multivariate data. And we also want to estimate probability in multivariate data space because the NCS is closely related to the contextual probability. So these are the two motivations. Okay, and to specialize the NCS for a type of data, we need to do a number of things. So the first one is we need to define the data space, and the second one is we need to define the neighborhood space. Okay. And then the third one is we need to interpret what it is. We need to know what it is we are defining. Okay, so in multivariate data space, and we begin with a set of variables or attributes, and each one has a domain like this. And we assume that the domain is finite for simplicity. And then we define the quantity like this. For each attribute, we define this. So if the attribute is nominal, then we use the power set of the domain. But if the attribute is ordinal, if it is ordinal, and then we define this quantity to be the set of all possible intervals.
Machine learning and signal.
Okay, so this is the set of all intervals that can be defined in the domain. Okay, and then the data space can be defined in this way. So that is simply the product of all the domains of the attributes. And so each element of the data space is called a simple tuple or a data tuple. And the neighborhood space is defined in this way. So it is simply a product of this quantity that I defined earlier. And each element is simply a vector of sets, And each element is called a hypertuple. And I will show example later on. And a simple tuple is a point in the data space, whereas a hypertuple is a rectangle in the data space. Now here is an example. If you look at the number C, so we have a data space, two-dimensional data space, and we have a number of sample data points, and we have a number of rectangles. Each rectangle is a hypertuple, and each point is a simple tuple. Okay, so that is a different way. The A and B, they are different way of representing simple and hypertuples. So B is a hypertuple, is a set of hypertuples. Okay, and then the NCM or the neighborhood counting metric, which was defined in one paper. So that is defined based on the multivariate data space omega and the associated neighborhood space. And then this metric is simply defined in this way. So that is the neighborhood counting measure, as we saw earlier on. So the definition is fairly simple. Then how to calculate this neighborhood counting metric? And so there is a theorem about this one, and it turns out so this one can be calculated through a simple formula. And so this one looks complicated because I wanted to be able to handle different types of attributes, numerical or categorical. And so for any data points x and y, each the NCM can be calculated in this way. It is simply the product of this quantity for each attribute. And this quantity can be calculated in this way. So that is the formula to calculate it if it is numerical, and that is the formula to calculate it if it is categorical. Okay, so that is the formula. And the complexity of this formula is in the same order as the Euclidean distance. So this I'm going to illustrate how to calculate the NCM. Let's consider one dimension. So that is a numerical attribute. And the data points are 1 and 3. And if we want to calculate the distance, then we calculate and we subtract. We calculate their differences. 3 minus 1. And for the NCM similarity, we simply count the neighborhoods. So we have neighborhoods, in this case, are intervals. So we have one interval, which is this, from 0 to 6. So this is one interval. And we have another interval from 1 to 6, another interval from 2 to 6, from 3 to 6. We have another interval from 0 to 5, and 1 to 5, 2 to 5, 3 to 5. And then we have 2 to 6, 2 to 5, and 2 to 4, 2 to 3, and so on. So we have so many different intervals. Then the common neighborhoods for 1 and 3 would include 1, 3, 1, 4, 1, 5, 1, 6, and 0, 3, 0, 4, and 0, 5, 0, 6. So that is the number of common neighborhoods. And this number is the NCM similarity. Okay, so this is the one-dimensional case. And this is a two-dimensional case. And in this space, and the NCS similarity. Okay, so in this case, we need to know what are the neighborhoods. And so each rectangle, on each rectangle is a neighborhood. So one neighborhood is this. This is one neighborhood. This is another neighborhood. That is another one. This is one neighborhood and another neighborhood. So every rectangle is a neighborhood. Then to calculate the neighborhood counting similarity between T and X, and all we need to do is to count the neighborhoods that cover both T and X. So in this case, this should be one neighborhood, and that is another neighborhood, another neighborhood, another neighborhood. And this can be calculated in this way. So if we know the neighborhood counting number for each dimension, and then we multiply the two numbers, that will give us the two-dimensional NCN. So for this dimension, it is 1 plus 1, 2, 3. So it is 3 in this dimension. And in the Y dimension, it is 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So the X dimension is 3, Y dimension is 4. So the C of T and X would be 3 multiplied by 4 to give us 12. So 12 should be this CTX, and then that one can be calculated similarly. Okay, and we can calculate the similarity as I showed earlier. But what if we want to estimate the probability in the same data space? Well, this can be done by simply calculating the C similarity between the T with every one of the data samples, every one of these which are given, and then we add them up. So if we want to calculate this one, then all we need to do is to calculate the C function for T and this, and T and this. Okay, and because this is conditional, so that quantity should be normalized again. And similarly for the minus class, all we need to do is to calculate the C function for T with this, and with every one of the negative class samples. And in that way, we will end up with a G probability, and that can be converted into the P probability through the linear relationship. Okay, so this one can be used to solve practical problems. So that is a tic-tac-toe game. So that is a data sample for the tic-tac-toe game. And so we have different board positions, and then we have the class labels, positive or negative. And if we want to solve this problem, and once again, we need to calculate the G probability, and G probability. And so that is the result of the calculation. And on the basis of this, and we can classify these two data points accordingly by using the Bayes classifier. So I'm not going to. So that is the intermediate result for calculating the G probability. Okay, I have actually evaluated this similarity metric on some public data sets. So these are public data sets in the UCI data repository. And so I used 3 versions of the k-nearest neighbor classifier. So this CW k-nearest neighbor, so that is the C value weighted k-nearest neighbor. So that is weighted k-nearest neighbor but weighting is done by the neighborhood counting similarity. So this is simply the k nearest neighbor with the distance metric provided by the Euclidean distance. Okay, so this is the Euclidean distance weighted k nearest neighbor. And clearly you can see that, so the CW k nearest neighbor give us consistently better result than the Euclidean distance based k nearest neighbor. And so that is different. So that is the statistics, some statistics numbers. So as the k value increases, then we can see a trend. Okay, I need to quickly move on to the next topic. Okay, the next topic is the neighborhood counting similarity for sequence. Okay, and so the motivation for this one is I want to specialize the generic neighborhood counting similarity to sequence data. And I also want to estimate probability in sequence data space. And so that is the simple motivation. As I mentioned earlier, to specialize the NCS for a specific type of data, we need to define the data space and the neighborhood space. So in the case of sequences, and the data space is simply the set of all sequences from a given alphabet. So we start with an alphabet which is similar to the attributes in the previous one. So we begin with an alphabet, then the set of all possible sequences definable from this alphabet would be our data space. And the neighborhood space, neighborhood can be defined in different ways, but one way is we can define the neighborhood to be a subsequence. So we begin with a sequence, and a neighborhood of this sequence could be one subsequence of the given sequence. And we can have many different subsequences resulting in different neighborhoods for each given sequence. Okay, and so once we have defined the data space and neighborhood space, and then we end up with the so-called the all common subsequences. So that is a specialization of the neighborhood counting for sequences. Okay, so the concept should be fairly straightforward. It is a specialization of the generic similarity for sequence. The important thing is how to calculate this quantity. So this is not so straightforward. We can certainly go take the brute force approach. We can consider all possible sequences, and then we check whether this one is a subsequence or not. And that is certainly not efficient. And it turns out we have efficient algorithms existing for calculating this quantity. So we have designed two algorithms. One is dynamic programming algorithm, and the other one is what we call the grid algorithm. And the dynamic programming and the algorithm works in this way. So we only need to specify the relationship between this. So I think I'm not in the position to, I don't want to go through the details. So that is the dynamic programming algorithm, and this is the grid algorithm. So that is quite looks quite complicated. Now let's take a look at a simple example. Here we have two sequences. This is one sequence. We have another sequence, and to calculate the ACS, or the all common subsequences, the similarity for these two sequences, we need to construct such a table. So we have the sequence in both dimensions, and then we index each position like this. And the matrix value would be calculated in this way. So the first row in the matrix and the first column of the matrix would be given as 1. So that is the default value. And then the remaining entries would be calculated according to these two conditions. So the corresponding and the symbols are equal, then that entry can be calculated from the previous entries in this way. We simply double this entry to give us a value for the new entry. But if these two quantities, these two symbols are not equal, then we calculate the value for this entry in this way. Okay. And let's take a look at this one. Take a look at this. And we need to compare this symbol and that symbol. And they are equal. So we can, so this value should be double this value, so which give us 2. Let's take a look at this entry. And this entry, we need to compare this symbol and that symbol. And Q is not the same as E. So we calculate the value for this entry by adding these two entries, and then we take away this entry. So that gives us 2. And let's take a look at this one, this entry, the last entry. And we need to compare this and that one. They are the same. So this value would be double of this. So that gives us 8. So that is the dynamic programming algorithm for the ACS similarity. Okay, so this one illustrates the grid algorithm. So we have 2 sequences like this, and then we begin with this. And if the common symbols will be represented by a dot, black dot, because here we have B is common in both sequences. We have a black dot, and here the A is common in this position for the 2 sequences. So each dot corresponds to one common symbol in both sequences. So that is the starting position. Then we draw arrows in the bottom right direction. The bottom right direction from every black dot. So from this black dot, we can draw an arrow to this one, because this one is to the right down. That is the bottom right direction. So we have an arrow here. So this one is also in the bottom right direction. We have an arrow. So this one is in the bottom right. We have an arrow as well. And this one is also in the bottom right. So we have arrow. So altogether, starting from this black dot, we have 4 arrows going out. And similarly for this one, we should have the 4 arrows going out from this as well. And actually each arrow will correspond to one common sequence. So when we count all of these arrows, we will end up with the ACS similarity. So that can be calculated through matrix operations. So that is the grid algorithms. Okay, in terms of the evaluation, so I have done evaluation of this similarity on one data set, which is the Australian Sign Language data set. So that is a well-known sequence data. So that is a sample of the sequence data. Here you can see that the sequences are the signs, and these sequences are of different length. They have different length, and that is the class labels, either happy or angry. Now here is the result. Here is the result. And the result, if you compare the numbers, so this line is what we need to do. ACS, so that is the ACS plus the NCM, that's the neighborhood counting. And so that gave us the best result. And take a look at this one, that is the ACS, and together with the NCM, that gave us the best overall result consistently. So my evaluation conclude that the ACS is quite competitive when we compare to the classical, the longest common subsequence similarity. So in the sequence analysis, the field long LCS, or the longest common subsequence, so that is well known and that is widely used similarity metric. And I have shown in this evaluation that ACS is actually better than LCS. Okay, so there are limitations of the original ACS algorithm. So that is repeating versus non-repeating. So the algorithm is valid only for sequences without repeating symbols. But this work, the work has been generalized to more general case of repeating sequences. And the original NCS algorithm has also been generalized to work on multidimensional sequences. Okay, and it has also been generalized to work on the 3 sequences or more sequences. You can compare a set of sequences, and that has been done. So these are the papers which publish the result in this direction. Okay, in summary about the sequence similarity. Okay, so we have demonstrated how a generic similarity can be specialized for sequence data. And in terms of the ACS similarity is conceptually novel and practically usable because we have efficient algorithms to calculate the ACS measure. And the ACS has displayed stable and competitive performance in classification, as shown in my evaluation. And the ACS has been extended for different type of cases under different constraints. Okay, the final topic is the specialization of the NCS for graph data. And so I'm conscious of time. I don't have time to go through the detail, but I would like to explain this work at a high level. Okay, so we know the graph is quite common. Graph is quite common, and the network analysis. So that is an active research area. But for example, in Twitter, LinkedIn, all of these have underlying graph structure or the network structure. And we usually want to analyze the networks, for example, to find a community in the network in order to understand the behavior of the people underlying the network. And the analysis is typically done by way of classification or clustering. But in these tasks, a key operation is to compare networks. And to compare a network is usually done through similarity. And we can do the cross-sectional comparison. We can compare one part of the network with another part, but we can also compare the network at one time with the network at a different time. And the motivation for this work is simply by the graph similarity. We know the graph similarity is quite important for graph analysis. And the graph similarity measures the degree to which 2 or more graphs are the same. And so this is typically done by graph matching. We want to match 2 graphs and then to see the degree of matching. And we can also do the graph transformation. We added one graph and to transform it into another graph. And the number of the editing operation would be regarded as a measure of the similarity. Okay, so the graph similarity is researched in different literature, in computer science and in other science and engineering field as well. So there are well-known solutions for graph similarity. For example, the graph edit, the graph kernel, maximum subgraph, and so on. But the better solutions are always desirable. If anybody can come up with a better solution in terms of the efficiency and effectiveness, then that is always welcome. And another motivation is, so these algorithms and the graph similarities are quite complex. It is quite difficult to implement these algorithms. Now the question is there a simpler algorithm that I can implement in hours rather than days? So that comes to the motivation. So the primary motivation is I want to specialize the NCS for graph data. I want to do probability estimation, and I want to simplify graph similarity. And again, I need to define the data space and the neighborhood space. And in this case, the data space is simply all possible graphs that can be constructed from a given node, given set of nodes and edges. So we begin with a set of nodes and the edges, and then the set of all possible graphs would be our data space. Then the neighborhood can be defined in different ways, but these are the examples. A neighborhood can be a subgraph. Given a graph, each neighborhood can be a subgraph. But its neighborhood can also be a path within this graph. And then the neighborhood space would be the set of all neighborhoods. And okay. Then my solution to this problem is, so I represent graph by adjacency matrices, and then the neighborhood is taken to be a path. Then the counting path through adjacency matrix multiplication. So to count and the number of paths existing in a given graph, and all I need to do is to multiply the adjacent matrix as many times as I like, until there's no point in doing further multiplication. And if I was given two graphs, and the similarity between two graphs would be regarded as the common path, the number of common paths, and the common path counting can be done via common adjacency matrix multiplication. So I begin with an adjacency matrix for each graph. I calculate their common adjacency matrix. And then I multiply this common adjacency matrix until all entries become 0. And I stop when the entries become 0. Then I add up the entries in the sequence of the adjacent matrix. So that will give us this count. Okay, so that is, we begin with graph, we represent it as adjacent matrix. And so that is adjacent matrix. I do the multiplication until all entries become 0. Okay, and then the algorithm can be simply done in this way. So that is the accumulation of all the adjacent matrix in the path, in the journey to do the matrix multiplication. And then at the end, I will have a matrix like this. So that contains the numbers that I need. When I add up all the entries in this matrix, that will give us the common path counts. Okay, so And so this is the efficient algorithm because that is the way to do the counting. But if you do the counting in the brute force way, then your complexity would be n to the power of 4. And then so we design an efficient algorithm which is more efficient, which is one order lower than that algorithm. So this is the algorithm. Okay, now it is now time to draw a conclusion. So this is my conclusion. Okay, the contextual probability is perceptionist as opposed to frequentist. So I have explained what I meant by perceptionist. And the contextual probability can be estimated through neighborhood counting. And neighborhood counting is a generic similarity kernel which serves as a methodology for designing new similarity measures for new type of data or to incorporate new constraints. Okay, it can be applied to different places, and that is the related work and that is future work. And I will stop here. Thank you very much.
Thank you very much, Professor Hu Wang, for this elaborative and innovative presentations. We learned so many new things, especially the concept of this perceptionist probability and neighborhood counting and its application in graph matching finding. Because this, what personally I found is the graph related problems are very complex problems, and we have to adopt the new approaches. So thank you very much. You have shown a path to us with this new approach. Now floor is open for question answer. Participants, if you have any question, please ask. Yeah.
Yeah, I think there's one question in the chat. Can neighborhood counting similarity be applied on proton data to find proton of similar functions? And the proton data, I understand that is a sequence data. That should be sequence data, and sequence data can be compared by the all common subsequences. And there are different versions of the ACS. Maybe I can go back to the earlier slides. Let me go back to the earlier slides. Okay, so that is okay. So the original ACS algorithm works on the non-repeating sequences, but we have actually extended the algorithm to work on sequences containing repeating symbols. If that is the case, we can still calculate the ACS. There's no problem. And then we can. So we have considered different constraints. For example, if you constrain the run length of a single symbol, say for example the symbol of A could appear consecutively a number of times, A, B, C, you can have such a sequence. That is the run length. If that is the case, you can use the sequence analysis method, which was discussed in one paper. And there are different versions. So I work with my collaborator, Professor Cees Alzinger, on quite a number of the scenarios where there are different constraints. And in those cases, the grid algorithm is is the method of choice, because that algorithm allows us to consider different arrows, and by default we only need to draw arrows in the bottom right direction of that matrix. And then if you have other constraints, you can constrain how the arrows are connected. So so at the moment, this doesn't allow me to show the references. So each number here corresponds to a paper. So we have published quite a number of papers on the sequence analysis to look at different constraints. I haven't actually used the sequence analysis algorithm on protein data by myself, but I understand that is sequence data, and I believe that is applicable to sequence analysis. Okay, thank you for the question. And let me see any. Okay, and how can I find the chat? Okay, and
if there is no question from participants, so we can conclude this session.
Okay, thank you.
Yeah, one more question. Can contextual probability be used for estimating the new emotion?
New emotion from
Yes.
various emotion signals. New emotion, estimating new emotion from various emotion signals. The contextual probability is, so this one, the contextual probability is a general probability estimation method. So I believe it can be used in the emotion estimation. So if you can formulate the emotion the problem as a classification problem, then yes, definitely contextual probability can be applied here. Thank you for the question. And so one line of my current work is to use the contextual probability for explaining decisions. So we build machine learning model to do classification, but how can we explain the classification? And we can explain in terms of identifying the attributes which have significant contribution to the classification. So that is the classical way of explaining machine learning predictions. But we can also explain our prediction by providing a confidence measure for the prediction. So this is what I'm currently working on, using contextual probability to come up with a more reliable confidence measure.
Okay, if no more question, yes. Thank you very much for this insightful presentation, and I hope all enjoy this presentation, as well as we have learned so many things, because what personally I found is so many things are new for us, especially how to fit into different application. And definitely the participants, mostly young researchers, which will benefited by this work, this presentation, and they will find it, they may apply this work into their problems. So thank you very much for taking time and sharing this insightful work with all of us. And now I would like to request all participants as well as Professor Hugh Wang for a group photograph. So all are requested to just on your camera.
Oh, right. Okay.
Yeah. One more
Let
thing.
Let me turn my direction so that it is brighter. At the moment, I think it is quite. Let me turn my direction.
Thank you. Yeah, one more thing. Professor Garg is also with us, and I would like to invite Sir to share a few words. Sir, please unmute yourself.
Okay.
Yeah, Professor Garg from University of Malta. I think Professor Pachori. Hello. Yeah, Professor Pachori. Hello, Professor Ambilas. Can you on your camera, please? Yes, sir. Lalit, sir.
Yeah. First of all, thank you very much indeed, Professor Wang, for giving such insightful and eye-opening talk, providing many new techniques and discussing their applications as well, especially practical aspects. Professor Wang is pioneer in this domain of machine learning, so there is a lot to learn from him, and I'm glad that he tried to summarize some of his work in these slides. But yes, I know there is far more to learn from him. So thank you very much indeed for inspiring all of us, Professor Wang. And I'm very much looking forward to meet you physically. This conference has been virtually, but next time possibly we will meet physically.
Please can you stop sharing, so it will be a
Okay. Let me stop sharing.
Yeah.
And I think let's stop share. Yeah.
Thank you.
Okay.
Thank you. Yeah. Professor Pachori. Hello.
Yes, Dr. Dilip.
Yes, you are
Yes,
traveling. Yeah, please on your video.
Yeah, good afternoon. Yeah.
Okay. Yeah, please, all are requested to switch on their video. Thank you. Yes, who's taking snap? Deepak?
Yes, sir.
Done?
Sir, one page done. Let me have the another.
Yeah. Please.
Done, sir.
Thank you. Thank you, everybody. Thank you, Professor Huming, sparing your valuable time, especially on Sunday. I know it was difficult because Sunday as well as some time zone difference. And I'm looking forward to have you physically sometime in future. So indeed, it was a very nice presentation as well as interaction. So thank you very much once again. On my personal behalf, as an organizing chair of this conference, as well as on behalf of my institute, National Institute of Technology, Raipur, thank you very much.
Okay, thank you. I do hope we can meet face to face sometime soon.
Sure. Yeah. Next conference, hopefully the situation will be normal, and we'll organize some activity. Definitely, we'll invite you again physically. Thank you, sir.
Okay, thank you
very much. Thank you, Garg sir. Thank you very much for joining. Professor Pachori, Professor Vivek, and many more faculty members, session chairs, those who have joined this session, especially I sent a message to join all. So all participants who are present in this session, this wonderful session, thank you very much. Thank you.
Okay, bye-bye.
Bye. Thank you.
Thank you, sir.
Thank you.